This is the second part of the hydrogen energy renewable sources. In this lecture, I want to discuss the hydrogen storage system, hydrogen transportation system, and the advantages and disadvantages of the hydrogen energy. The hydrogen storage system, speaking of its natural occurrence, it is the most abundant element in the universe. The sun and the other stars are composed largely of hydrogen. Astronomers estimate that the 90% of the atoms in the universe are hydrogen atoms. Hydrogen is a component of more compounds than any other element. Water is the most abundant compound of the hydrogen found on the earth. Molecular hydrogen is not available on earth in conventional natural reservoirs. Most hydrogen on earth is bonded to oxygen in water and to carbon in live or dead or fossilized biomass. It can be created by splitting the water into the hydrogen and oxygen. Water is again formed when the hydrogen is used. On the other hand, its preparation could be done by breaking the chemical bonds from the compounds. A few common methods include the electrolysis from steam and hydrocarbon or carbon reaction of metals with acids, ionic metal hydrides with water, etc. Currently, the global hydrogen production is 48% from the natural gas, 30% from the well, and 18% from the coal. Water electrolysis accounts for only the 4%. Its storage is important because it has wide range of applications. They range from stationary power, portable power to transportation, etc. Also, it has the highest energy per mass of any. However, its low ambient temperature density results in a low energy per unit volume, therefore requiring the development of advanced storage methods that have potential for higher energy density. Hydrogen can be stored physically as either a gas or a liquid. Storage of hydrogen as a gas typically requires high pressure tanks. Storage of the hydrogen as a liquid requires the cryogenic temperatures because the boiling point of the hydrogen at 1 atmosphere pressure is minus 250.8 degrees centigrade. Hydrogen can also be stored on the surfaces of solids by absorption method or within the solids by the absorption method. Now the hydrogen can be stored as the compressed hydrogen. The compressed hydrogen is a storage form whereby the hydrogen gas is kept under the pressures to increase the storage density. Compressed hydrogen in hydrogen tank at 350 bar and the 700 bar is used for hydrogen tank systems in vehicles based on the type 4 carbon composite technology. Car manufacturers have been developing this solution such as Honda or Nissan. Another storage form is the liquefied hydrogen. The liquefied hydrogen tanks for cars producing, for example, the BMW hydrogen. Japan has a liquid hydrogen storage site in Kobe Port. Hydrogen is liquefied by reducing its temperature to minus 253 degrees centigrade, similar to liquefied natural gas, that is called LNG, which is stored at minus 162 degrees centigrade. A potential efficiency loss of 12.79% can be achieved, or 4.26 kilowatt hour per kg out of 33.3 kilowatt hour per kg. Now come to the chemical storage of hydrogen. The chemical storage could offer high storage performance due to the high storage densities. For example, the supercritical hydrogen at 30 degrees centigrade and 500 bar only has a density of 15 mole per liter, while the methanol has a density of 49.5 mole per mole hydrogen per liter methanol, and saturated dimethyl ether at 30 degrees centigrade and 7 bar has a density of 42.1 mole hydrogen per liter dimethyl ether. The another storage system of the hydrogen is metal hydrides. The metal hydrides such as magnesium hydride, sodium aluminum hydride, lithium aluminum hydride, lithium hydride, LaNi5H6 and the TiFeH2, ammonium borate, boron and the palladium hydride represent the source of the stored hydrogen. Again, the persistent problems are the percentage of weight of hydrogen that they carry and the reversibility of the storage process. Some are easy to fuel liquids at the ambient temperature and pressure, whereas others are solids which could be turned into pellets. These materials have good energy density, although their specific energy is often worse than the leading hydrocarbon fuels. Another source is the storage system is the aluminium. The hydrogen can be produced using the aluminium by reacting it with water. To react with the water, however, the aluminium must be stripped of its natural oxide layer, a process which requires the pulverization, chemical reactions with caustic substances or alloys. The byproduct of the reaction to create the hydrogen is aluminium oxide, which can be recycled back into the aluminium with the Hall-Heroult process, making the reaction theoretically renewable. However, this requires the electrolysis, which consumes a large amount of organic hydrogen carriers. Unsaturated organic compounds can store the huge amounts of hydrogen. These liquid organic hydrogen carriers are hydrogenated for storage and hydrogenated again when the energy or the hydrogen is needed. Using the LOHCs LOHCs mean liquid organic hydrogen carriers. Relatively high gravimetric storage densities can be reached about 6 Wt percentage, and the overall energy efficiency is higher than for other chemical storage options such as producing methane from the hydrogen. Both the hydrogenation and the dehydrogenation of the LOHCs requires catalyst. It was demonstrated that replacing hydrocarbons by heteroatoms like N, O, etc. improves the reversible dehydrogenation or the hydrogenation properties. Another storage form is the formic acid. The formic acid is a highly effective hydrogen storage material, although its hydrogen density is very low. Carbon monoxide free hydrogen has been generated in a very wide pressure range 1 to 600 bar. A homogeneous catalytic system based on the water soluble ruthenium catalyst selectively decompose the HCOOH into the hydrogen and carbon dioxide in aqueous solution. This catalytic system overcomes the limitations of the other catalyst, just like poor stability, limited catalytic lifetimes, formation of carbon monoxide, for the decomposition of the formic acid, making it a viable hydrogen storage material. And the co-product of this decomposition, the carbon dioxide, can be used as the hydrogen vector by the hydrogenating it back to the formic acid in a second step. The catalytic hydrogenation of carbon dioxide has long been studied and efficient procedures have been developed. Formic acid contains the 53 gram per liter hydrogen at room temperature and atmospheric pressure. By the weight, the pure formic acid stores 4.3 weightage of percentage hydrogen. Pure formic acid is a liquid with a flash point of 69 degrees centigrade. With reference to the gasoline is minus 40 degrees centigrade. Ethanol is 13 degrees centigrade. The 85% formic acid is not flammable. Second, next type of storage system is the carbohydrates. Carbohydrates, the polymeric C6H10O5 releases the hydrogen in a bioreformer mediated by the enzyme cocktail cell-free synthetic pathway biotransformation. The carbohydrate provides the high hydrogen storage densities as a liquid with the mild pressurization and the cryogenic constraints. It can also be stored as a solid powder. The carbohydrate is the most abundant renewable bioresource in the world. Porous or the layer carbon. Activated carbons are highly porous amorphous carbon materials with the high apparent surface area. Hydrogen physical absorption can be increased in these materials by increasing the apparent surface area and optimizing pore diameter of around 7 angstrom. These materials are of the particular interest due to the fact that they can be made from the waste materials such as cigarette butts, which have shown great potential as the precursor materials for high capacity hydrogen storage materials. Graphene can store hydrogen efficiently. The hydrogen adds to the double bonds giving graphene. The hydrogen is released upon the heating to 450 degrees. The porous or layer carbon hydrogen carriers based on the nanostructure carbon such as carbon buckyballs and nanotubes have been proposed. To realize the carbon materials as effective hydrogen storage technologies, carbon nanotubes have been doped with the magnesium hydride. The proposed mechanism involves the creation of fast diffusion channels by the carbon nanotubes within the magnesium hydride lattice. Fullerene is the other carbonaceous nanomaterials that has been tested for hydrogen storage in this center. Fullerene molecules are composed of a C60 closed cage structure that allows for the hydrogenation of the double bonded carbons, leading to a theoretical C60H60 isomer with a hydrogen content of 7.7 weightage percentage. However, the release temperature is these systems is very high, on about 600 degrees centigrade. Another storage system is the metal organic framework. The metal organic frameworks represent another class of synthetic porous materials that store the hydrogen and energy at the molecular level. The MOFs are metal organic frameworks are highly crystalline inorganic organic hybrid structures that contains the metal clusters or ions as nodes and the organic ligands as linkers. When the guest molecules, which are called solvent, occupying the pores are removed during the solvent exchange, and heating under the vacuum porous structure of the MOFs can be achieved without destabilizing the frame, and the hydrogen molecules will be absorbed onto the surface of the pores by physioabsorption. Compared to the traditional zeolites and the porous carbon materials, the MOFs have very high number of pores and surface area, which allow the higher hydrogen uptake in a given volume. Thus, the research interest on the hydrogen storage in MOFs have been growing since 2003, when the first MOF-based hydrogen storage was introduced. Since there are infinite geometric and chemical variations of the MOFs based on the different combinations of SBUs and linkers, many researchers explore what combination will provide the maximum hydrogen uptake by varying the materials of the metal ions and the linkers. In 2020, the researchers at the Northwestern University in USA reported that the NU-151A1, an ultra-porous metal organic framework based on the metal trinuclear clusters, yielded impressive gravimetric and volumetric storage performances for the hydrogen and the methane, with a hydrogen delivery capacity of 40% and the 46.2 gram per liter. Now come to the second part, that is the hydrogen transport system. The hydrogen is easy to transport, easy in long distance, and can be transported in different formats. Today, the transport of the compressed gaseous or liquid hydrogen by lorry, of compressed gaseous hydrogen by pipeline to the selected locations are the main transport options are used. The most common hydrogen transportation means covering the needs of the different hydrogen markets, such that the compressed gas cylinders or the cryogenic liquid tankers, pipelines, blending with the natural gas. Now the first type is the compressed gas container. Gaseous hydrogen can be transported in small to medium quantities in compressed gas containers by lorry. For transporting the larger volumes, the several pressurized gas cylinders or tubes are bundled together on so-called CGH2 tube trailers. The large tubes are bundled together inside a protective frame. The tubes are usually made of steel and have a high net weight. This can lead to the mass-related transport restrictions. The newest pressurized storage systems use the lighter composite storage containers for the lorry transport. The low density of hydrogen also has an impact on its transport. Under standard conditions 1.013 bar and 0 degree centigrade, the hydrogen has a density of 0.0899 kg per cubic meter, also called the normal cubic meter, NM3. In hydrogen is compressed to 200 bar, the density under standard conditions increases to 15.6 kg hydrogen per cubic meter, and at 500 bar it would reach 33 kg hydrogen per meter cube. A tube trailer cannot store compressed gas as compactly as a tanker for liquid fuels. This means that the available tank volume for hydrogen per tanker is very lower. Single tube trailers carry approximately 500 kg of hydrogen depending on the pressure and container material. The largest tank volumes for gaseous hydrogen transport are currently 26 cubic meters. Taking account of the low hydrogen density factor at 500 bar, this results in a load of around 1100 kg hydrogen per lorry. This figures extrapolates to approximately 12,000 normal cubic meters of hydrogen. At 250 bar, both the weight of the hydrogen and its transport volume in nanometer normal meter cube would be roughly halved. Liquid transport. As an alternative, hydrogen can be transported in liquid form in lorries or other means of the transport. In comparison to pressure gas vessels, more hydrogen can be carried with an LH2 trailer, as the density of liquid hydrogen is higher than that of the gaseous hydrogen. Since the density even of the liquid hydrogen is well below that of the liquid fuels at approximately 800 kg per meter cube. In this case, too many relatively moderate masses of hydrogen are transported. At a density of 70.8 kg per meter cube, around 3,500 kg of liquid hydrogen, or almost 40,000 normal meter cube, can be carried at a loading volume of 50 meter cube. Over the longer distances, it is usually more cost effective to transport the hydrogen in liquid form, since a liquid hydrogen tank can hold substantially more hydrogen than a pressurized gas tank. For the purpose of the liquid transport, the hydrogen is loaded into the insulated cryogenic tanks. LH2 trailers have a range of approximately 4,000 km. Over the journey time, the cryogenic hydrogen heats up, causing the pressure in the container to rise. Similarly to lorry transport, LH2 can also be transported by ship or by rail, provided that the suitable waterways, railways lines, and the loading terminals are available. Second one is the pipelines. A pipeline network would be the best option for the comprehensive and large-scale use of the hydrogen as an energy source. However, the pipelines require the high levels of initial investment, which may pay off, but only with the correspondingly large volumes of hydrogen. Nevertheless, one possibility for developing pipeline networks for hydrogen distribution is local or regional networks known as the micronetworks. These could subsequently be combined into the trans-regional network. Worldwide, there are already more than 4,500 km of hydrogen pipelines in total, the vast majority of which are operated by hydrogen products or hydrogen producers. The longest pipelines are operated in the USA in the states of Louisiana and Texas, followed by the Belgium and Germany. Last type of transport system is the blending with the natural gas. The blending hydrogen into the natural gas pipeline networks has also been proposed as a means of delivering pure hydrogen to markets. Using the separation and purification technologies downstream to extract the hydrogen from the natural gas blend close to the point to end use. As a hydrogen delivery method, blending can defray the cost of building dedicated hydrogen pipelines or other costly delivery infrastructure during the early market development phase. Infrastructure elements that were installed at the time, such as pipelines, gas installations, seals, gas appliances, etc., were designed for the hydrogen-rich gas and were later modified with the switch to the natural gas. Many countries have looked at adding the hydrogen into the existing natural gas. Now come to the last part of my lecture, that is the advantages and disadvantages of the hydrogen energy. First come to the advantages. It is readily available. It is a basic earth element and is very abundant. However, it time consuming to separate hydrogen gas from its companion substances. While that may be the case, the results produce a powerful clean energy source. It does not produce harmful emissions when it is burned. It does not emit harmful substances. Basically, it reacts with the oxygen without burning, and the energy it releases can be used to generate electricity, used to drive an electric motor. Also, it does not generate carbon dioxide when burned, not unlike other power sources. Third one is it is environmentally friendly. It is a non-toxic substance which is rare for a fuel source. Others such as nuclear energy, coal and the gasoline are either toxic or found in the places that have hazardous environments. Because of hydrogen is friendly towards the environment, it can be used in ways that other fuels cannot even possibly match. Fourth one is it can be used as fuel in rockets. It is both powerful and efficient. It is enough to provide power for powerful machines such as spaceships. Also, given that it is environmentally friendly, it is a much safer choice compared to the other fuel sources. A fun fact that the hydrogen is 3 times as powerful as gasoline and other fossil fuels. This means that it can accomplish more with less. Fifth one is that it is fuel efficient compared to the diesel or gas. It is much more fuel efficient as it can produce more energy per pound of fuel. Hydrogen powered fuel cells have 2 or 3 times the efficiency of traditional combustion technologies. Hydrogen fuel cells are capable of generating electricity of up to 65% efficiency, whereas a conventional combustion based power plant usually generates electricity between 33 to 35% efficiency. Sixth one is it is renewable. It can be produced again and again, unlike other non-renewable resources of energy. This means that with the hydrogen you get a fuel source that is limited. Basically, the hydrogen energy can be produced on demand. Now come to the disadvantages. The first disadvantage is that it is very much expensive. While widely available, it is expensive. A good reason for this is that it takes a lot of time to separate the element from the others. If the process were really simple, then a lot would have been doing it with the relative easy, but it is not. Although the hydrogen cells are now being used to power hybrid cars, it's still not a feasible source of fuel for everyone. Until the technology is developed that can make the whole process a lot more simpler, then the hydrogen energy will continue to be an expensive option. Second one is that it is difficult to store. Hydrogen is very hard to move around. When speaking about oil and the element can be sent through the pipelines. When discussing coal, that can be easily carried off on the back of the trucks. When talking about the hydrogen, just moving even small amounts is a very expensive matter. For that reason alone, the transport and the storage of such substance is deemed impracticable. It is not easy to replace the existing infrastructure. The gasoline is still being widely used to this way nowadays, and as of the moment there just is not any infrastructure that can support hydrogen as fuel. This is why it becomes highly expensive to just think about replacing gasoline. Also, the cars need to be refitted in order to accommodate the hydrogen as fuel. It is highly flammable also. So since it is a very powerful source of fuel, the hydrogen can be very flammable. In fact, it is on the news frequently for its many number of risks. Hydrogen gas burns in air at very wide concentrations between 4 to 75%. It is dependent on the fossil fuels. Although the hydrogen energy is renewable and has minimal environmental impact, other non-renewable sources such as coal, oil and natural gas are needed to separate it from the oxygen. While the point of switching to hydrogen is to get rid of using fossil fuels, they are still needed to produce hydrogen fuel. So that's all about on the hydrogen energy resources. These are the references from where I made this tutorial. You should go through these references for more knowledge. Thank you very much.